Hi, I'm Matthew Zhu, and this is my Lab 1 charge tape slide deck. So just a quick introduction. The purpose of this lab was to observe the interaction between two strips of charged tape and to determine the charge of the tape. We were then to create a simulation to model this interaction. Some physics principles used, mainly the equation for electrostatic force, and a quick sneak peek at the outcome was that the tape was found to be positively charged and that the 20 centimeter piece of tape had the charge listed below. Just a couple quick terminology that's going to be used for the rest of the video. The electrostatic force equation, obviously to your right, and the resulting force due to gravity at sea level. One important thing I want to point out is that the charge of an electron is around negative 1.6 times 10 to the negative 19 coulombs. So some initial assumptions for the setup, that the tapes were the exact same dimension. This would allow us to treat them with the exact same charge. The charge tapes can also be treated like point charges. The assumption there is that the charge is evenly spread across the tape. And two more important assumptions was that the tape was held parallel to one another and that there was no interference or loss of charge from the hands. So some initial observations. The tape seemed to be positively charged because it was attracted to a negatively charged pen, which was rubbed in our hair. And it seemed that 2 centimeters of separation was needed to float the suspended tape. For the calculations, we know that because the tape is levitating and not accelerating, that the net force on it is equal to 0, and that would therefore mean that the force of gravity, at least the magnitude, is equal to the magnitude of the electrostatic force. So you see us set up that relation directly to the right, and if you note, the charge is squared here because we assume that the two pieces of charged tape have the exact same charge because they have the exact same dimensions. The tape is around 1 gram per meter, and therefore that's how we get the weight that's listed to the right. And the width of the tape was around 1.9 centimeters, and this allows us to calculate the surface area of the tape. And then with the area of an atom, we can figure out how many atoms are on the surface of the tape, and then that allows us to find the ratio of electrons to atoms on the surface of the tape. So here's the simulation results and a little bit of the code. On the right, you'll see that the simulation nets us around the same charge that we found by hand calculations. If you look to the left, you'll see the actual code of the simulation. In the first 13 lines, we basically just initialize some values. So what's important here is the length of the tape. That is basically all we need aside from the distance that they were held apart. And then the rest of the code basically calculates the charge required in order for the length of the tape that was given and the distance that was observed. The length of the tape is important because that nets us the mass. As you can see, what was given was that 1 meter of tape was around 1 gram, and this allows us to calculate the mass of the tape given the length. So some possible sources for error. One was that the charged tape was not actually a point charge. Different intervals of tape could experience different force depending if the charge was not spread evenly. Another source of error was that the tape lost charge due to the hands holding it or the objects that it was taped to. Another assumption was that electrons cannot pass across the tape and that the tape was held perfectly parallel. If the tape was not, then uneven force again would net a different result. And some what-if questions. If positive charges and protons had negative charge, really wouldn't change anything because these are just names to begin with. They would still interact the same way. Same charges would still repel each other. It's just the masses of the charges would be wildly different. It is important to handle the charged tapes as little as possible because electrons can move from your hands or other objects onto the tape, as we saw, the tape was positively charged, meaning it was lacking electrons. If electrons moved from your hands onto the tape, it would neutralize some of the positive charge of the tape, giving you inaccurate measurements as to what the tape's charge actually was after treatment. So the conclusion is that the computational model was accurate and that the charge tapes can largely be treated as point charges, as we saw that the model predicted a very similar amount of charge to what we actually observed. Thank you.